right, welcome back. So we'll continue talking about chapter 21. I'm recording on a new iPad, so yay. We'll see how that goes, and hopefully the microphone works a little better. I don't have a little earpiece Bluetooth microphone thing, so we'll see how it goes. Anyway, we'll continue in chapter 21 talking about coordination compounds. In particular, I want to look at isomers. Figure 21.8 kind of maps out how isomers are related. So I thought I'd draw that on the board here in bits and pieces and add in definitions and examples. So what are isomers? Well, isomers have the same formula but different structures. These are compounds with, so we'll say here, same formula, different structures. Okay. Now, there are two major classes of isomers. We have the structural isomers, where the atoms are linked together in a different order. So atoms linked together differently. The other major class of isomers are stereoisomers. And stereoisomers have the same connectedness, but they have a different arrangement of the atoms in space. So atoms arranged differently in space. And we'll look at some examples of each of these in just a little bit. Sometimes I say that structural isomers, instead of saying the atoms are linked together differently, I say they have different connectivity. So maybe I'll add that in here, different connectivity. And again, stereoisomers, we'll see we have a different arrangement in space. So again, you can refer to figure 21.8, and this is just the beginning of it. I'll erase, I'll pause here in case you want to pause and jot this down. All right, so let me erase and we'll continue. We'll focus on structural isomers first. And I will refer to different figures in the text, and I forget the exact numbers, so I'll have to look at them, but I'll jot those down for you. So if you have the text with you, you have the ebook, you can take a look at those, because isomers are best understood by looking at them, by visualizing them. And actually for the stereoisomers, I'll show you guys models, and building models can be helpful. But first, let's look at structural isomers. All right, so this was that left-hand branch of that diagram. Now, one type of structural isomer that we have is what we call coordination isomers. And if you recall, when we have a coordination compound, we have a complex ion and then counter ions. The stuff within the complex ion is called the coordination sphere. So we could have, just as an example, Eg, we could have, let's do chromium. I have my notes here. Pentaamine chromium. And we'll do sulfate, so 4 Br. Okay, so in this case, we've got a pentaamine sulfonato chromium 3 bromide. It's chromium 3 because we have a 2 minus here, so it has to be net plus 1 to have the 1 bromide there. Anyway, if we swap these two guys, the bromine and, or the bromide and the sulfate, we would have then have a pentaamine bromo chromium 3 sulfate. So we've essentially just switched the bromide and the sulfate. So here, the first one, the bromide is the counter ion. The sulfate's in the complex ion, in the coordination sphere. And the bottom one, now the bromide is a ligand in the coordination sphere, and the sulfate is outside as a counter ion. All right, so those are coordination isomers, and they're easy enough to see just by the formula here. We don't really need to draw their structures. We have another type of isomer called a linkage isomer. Just make that a capital I, like before. And linkage isomers, we have the same ligand attached by different atom. And so the example in the text will have some metal, and we'll have, for example, NOO versus metal attached to ONO, like that. And so this would be metal, NO2, and this would be metal, the parentheses are not around the M. This would be metal ONO, like that. So here, writing it in the formula like this tells us that the structure is actually this one here. The nitrogen is the one that donates the lone pair to form that coordinate covalent bond. And the other one, our metal ONO, it's one of the oxygens. We could see this in another example, which I'll go ahead, I'm going to erase this. It is in the text, figure 21.9. Just write that here, figure 21.9. And so we could have our metal, and then C triple bond N versus metal N triple bond C with a lone pair there. So now if I take my metal here, and what's my first one? The carbon. So I've got a couple of, these are a couple of cyanide ions here. And so the black is the carbon and the blue is the nitrogen. And so, and then we've got a triple bond between the two. I'll go ahead and link up my metal here to my carbon. So now this is metal. Let me flip it over. There we go. Now it looks like that. Metal, and then here's my coordinate covalent bond between the carbon, of the cyanide and the metal. Now you can contrast that to having it attach the other way. So like this, where now coordinate covalent bond is attached to the nitrogen of the cyanide. And let me just grab another carbon here, not carbon, sorry. Pretend metal. See, black is usually carbon, but I didn't have enough metal ones because I'm going to use more in the next video. Anyway, we can see on the top we've got the coordinate covalent bond between the carbon and the metal, and on the bottom it's between the nitrogen and the metal. So these are what we would call linkage isomers. That's all I'm going to do for this video. In the next one, we'll take probably a lot more time and look at stereoisomers, where we really will need to start thinking in 3 dimensions. So I guess I will talk with you later.